Hello and welcome. Let us recall impulse function or delta t, which we can think as a very narrow pulse like this, starting from minus a by 2 up to plus a by 2, and the height is 1 over a, so the area is 1, and we take the limit a tending to 0. Now a delta t or impulse function need not be a rectangular pulse like this. We can also think of a triangular pulse, which is like this. Say it starts from minus a by 2 and stops at plus a by 2. The height is 2 by a. Therefore, the area will be half into base into height, which is equal to 1. And once again, if you take the limit a tending to 0, this will also give us a impulse function or delta function. Because you recall that delta function mathematically defined as being equal to 0 if time is not 0 and the integration of delta t dt from minus infinity to plus infinity is equal to 1. Both these functions, rectangular or triangular, both of them satisfies this definition. Similarly, you may think of a Gaussian pulse, which looks like this. It gradually becomes 0 asymptotically, and the functional form of this signal is like this: 1 over root 2 pi a e to the power minus, say, t square by 2 a square. And if you take smaller and smaller value of a, then this pulse will be narrower and narrower. Simultaneously it will be taller also. If you take the limit a tending to 0, this will also give a delta function. And mathematically one can prove that the area under this curve is 1. So delta function in general can have any arbitrary form like any of this, as long as it satisfies the area under this is 1 and the function is 0 if you look at any point away from the origin. Now let us consider the derivative of delta t, delta dot, or ddt of delta t. If you consider a narrow rectangular pulse with the width being very narrow and height being very tall, if this is delta t, then if you differentiate this function with respect to time, then at this edge there is a rising edge, so you will get, if you think this as a step jump, then the derivative will be a impulse like function at this point, very narrow pulse, and then at this point there is a negative step jump, so there will be a negative impulse like function. This is how you may imagine or try to visualize delta dot t. You may also consider the triangular pulse with the width being very narrow. Then if you differentiate this function, then on the left side you will get a positive slope like this, and on the right side you will have a negative slope like this, and this is how you may imagine the derivative of delta function. That's for your visualization. Now let me give an important property of delta dot. If you have any function x of t, and if you multiply it with delta dot t, and if you integrate it over minus infinity to plus infinity dt, which is also same as integrating this function within 0 minus and 0 plus, because beyond that this function is 0. Now this integration you can carry out by parts. So consider this as the first function and delta dot as the second function. So we will have first function integration of the second, which is delta t evaluated at minus infinity and plus infinity, minus integration of x dot delta t dt from minus infinity to plus infinity. Now this part will become 0 because at plus or minus infinity delta function is 0, and this part, if you consider x dot as a function multiplied with delta t, then if you recall what we learned earlier, you can write this part as x dot at the point 0. So this is an important property of delta dot function. So integration of xt delta dot t dt is equal to minus x dot 0. However, recall that xt delta t integrated from minus infinity to infinity gives x of 0. So from these two we can say that delta t and delta dot t are not same. Similarly, you can imagine or think of delta double dot, delta triple dot, etc. That is your home task. Imagine second derivative, third derivative of the impulse function. Okay. Now we were studying linear differential equations, and today we shall learn how to solve such differential equations when the input is an impulse function delta t. Let us learn this with an example. Suppose this is a given differential equation where the input is given to be delta t in the question, and also the initial conditions are given. We need two initial conditions since this is a second order system, and suppose they are y0 minus equal to 1 say, and y dot 0 minus equal to 2. Now please note that the impulse function delta t is a very narrow pulse occurring at t equal to 0. You can think that this starts at 0 minus and stops at 0 plus. Therefore, the initial conditions are given at the moment when the input just starts. That means before the input can have any effect, or before the input can change the output or the system. Okay. Now also note that the input x or delta t is actually equal to 0 for time greater than equal to 0 plus. Therefore, this problem will be easy to solve for the time interval starting from 0 plus up to infinity, because then the input is 0. Only within this small region 0 minus and 0 plus, it is slightly difficult to solve this equation. So we shall solve this problem in two parts, two steps. First we shall solve within the region or time interval 0 minus to 0 plus, and then we will solve from 0 plus up to infinity. These are the two steps. Let us perform step 1. For that, let me rewrite or copy this equation. Before we solve it, let us make some observations. First of all, in this equation, the right hand side has an impulse signal. So for this equality to hold, left hand side must also have an impulse signal within this narrow region of 0 minus and 0 plus. Otherwise this equality will not hold. Now the impulse signal in the left hand side might come from y, or it might come from the derivative of y, or from the second derivative of y. Now the second observation is that y must be continuous in this region, 0 minus to 0 plus. That means y cannot have any step jump. Why? Because if y has a step jump, then when you differentiate y, you will get a delta function. And when you differentiate that delta function again, that means the second derivative, you will get delta dot. So on the left hand side you will have a delta dot, but on the right side there is no delta dot. Right side has only delta, and delta dot, they are not same. So we cannot have a delta dot on the left side. That means y cannot have any step jump. So y cannot have a step jump. Similarly, this function y cannot have a delta function. I mean, y cannot be a delta function, because if y is a delta function, then this first derivative will be delta dot, second derivative will be delta double dot, but on the RHS there is no delta dot or no delta double dot. So y cannot have a impulse function in it, or y cannot be a impulse function. So y cannot have a step jump, y cannot be a impulse signal. Now with these observations, let us proceed by integrating this equation, the both sides of this equation. Copy, paste. Let me integrate both the sides with respect to time from 0 minus to 0 plus. This side also integrated over time. But right side is equal to 1 because the area under the delta function is 1. Now the left side can be written as this, where I will write this second derivative as d dt of dy dt. Now let us split these three terms and integrate them one by one. So LHS has three integrations. Now this derivative and integration will cancel, and it will become dy dt, putting the limit 0 plus and 0 minus. Then the next term will become y from 0 minus to 0 plus, plus this term. Now note that this term is equal to y of 0 plus minus y of 0 minus, and that is equal to 0, because we have already said y cannot have any step jump within this small region. Therefore, y should be continuous and its value should be same before this before 0 and after 0. So this term will become 0. Then this term will also become 0 because y cannot have a delta function in it, and other than delta function, any normal function, when you integrate within a very small region, that will become 0, because this is same as the value of y at that point multiplied by dt with the limit dt tending to 0. So this will also be 0. And now consider the first term. The first term we will write as dy dt at 0 plus minus dy dt at 0 minus. So this gives, which means dy dt at 0 plus will be equal to 1 plus dy dt at 0 minus. Now dy dt at 0 minus is given in the question. Its value is 2. So this will become 1 plus 2 equal to 3. So we got y dot 0 plus is equal to 3, and we already know that y 0 plus is equal to y 0 minus, which is given in the question as 1, because we have argued y should be a continuous function. Okay, so now that was our step 1. So in step 1 we have got the value of y 0 plus equal to 1 and y dot 0 plus equal to 3, which we shall use in step 2. That means we will solve within the region 0 plus up to infinity. Now let me copy the differential equation. Within this region, x is equal to 0. So we know that the solution of this equation will be a complementary solution of this equation, and if we factorize the left hand side, we can write dy dt plus 2 multiplied by dy dt plus 3 equal to 0. So the two roots of this equation are minus 2 and minus 3. So y will be of the form some k1 multiplied by e to the power minus 2t plus k2 e to the power minus 3t, with the initial condition that y0 plus, that means at the beginning of this particular interval we are considering, at the beginning the value of y is 1 and y dot is 3. Now you know how to proceed. Differentiate this equation. From here you can write dy dt is equal to minus 2k1 e to the power minus 2t minus 3k2 e to the power minus 3t. Then you put the value t equal to 0, so we shall get y dot 0 is equal to minus 2k1 minus 3k2, and this is equal to 3. And if you put in this equation t equal to 0, then we will have y0 is equal to k1 plus k2. This is given as 1. We will put y equal to 0 plus actually. Okay. And now if you solve these two equations, and you shall get k1 equal to 6 and k2 equal to minus 5. Okay, so that process was easy, but let us review what we actually have done. This is the given differential equation with the initial conditions y0 minus equal to 1 and y dot 0 minus equal to 2. So this is the impulse or input pattern. At the moment when this input starts, 0 minus, the output has a value of 1 and a slope of 2. And then within this narrow region, we actually did not try to find out a functional form or mathematical expression for y. Instead, we logically argued that y should be continuous, and so after this narrow interval the value of y should remain 1. And we calculated that after this interval the slope of y will increase and become 2. Okay? Now we got y0 plus equal to 1 and y dot 0 plus equal to 3. Using this value, we have solved the differential equation from here up to infinity using normal procedure. We needed to perform step 1 before solving in this region, because while we solve for yt within 0 plus to infinity, we need the starting value or the initial value in this region, that is y0 plus and y dot 0 plus. Therefore, in the first step, we have calculated y0 plus and y dot 0 plus from the given y0 minus and y dot 0 minus. Here in a plastic container containing some water, I have a floating. Suppose this position of the float is y equal to 0 and y increases from left to right. Now with a pen I will give a impulse force towards the right on this float like this. Here I push it. So the float starts to move towards the right and it gradually slows down and then it stops. Now it is already stopped. So this is the y direction, and if I plot time vertically, then just before the push the float was here, just after the push the float was still here, and then it gained some speed and it started to move with time, and finally it reached this position. Initially it had a higher velocity and the velocity then reduced and finally it became 0, and now it will stay there continuously. Let us now try to explain this experimental observation mathematically. We have this water in a container with this float floating on it. Let the mass of the float be m. The force acting on it from outside is xt, so that is the external force, and the displacement is denoted as y. Now there will also be another force acting on this float when this float moves, that is the viscous force or viscous drag, and we will assume that this viscous force is proportional to the speed of the object dy dt multiplied by some constant, viscous constant, and let's put a minus sign to indicate that this force acts in the direction opposite to the velocity or speed. If the speed is towards the right, then the force will be towards the left. So the total force acting on this float is external force xt minus viscous force, and this total force should be equal to the mass times the acceleration of the object. From this we can write this differential equation relating the output y or displacement to the input force, external force xt, and we have initial conditions that y of 0 minus was 0 and y of y dot of 0 minus was also 0. Initial position and velocity both were 0. We have given a impulse force, so let this xt be delta t. This delta t starts to act at 0 minus, and at that moment when input begins, velocity and position both are 0. Now let us try to solve this equation, and as usual we will solve this equation in 2 steps. Step 1, we will argue that y0 plus should be equal to y0 minus, that means 0, because y must be continuous. If y is not continuous, then the derivative, then y can have a step jump, and then the derivative of y in this equation will be an impulse function, and the second derivative will be delta dot. But the right side of this equation has no delta dot, so y cannot have any discontinuity or step jump. So y0 plus must be 0. Then let us integrate this equation both the sides, and we can write integration of m, this term will be like this, plus k integration of dy dt from 0 minus to 0 plus, and the right side will be integration of delta t which is equal to 1. Now this first term you can write as dy dt with limits 0 minus and 0 plus multiplied by m plus k multiplied by, this will be y 0 plus 0 minus, this is equal to 1. Now since y0 plus and y0 minus are equal, therefore this term will be 0, and we have m dy, so you can write this as y dot 0 plus minus y dot 0 minus is equal to 1. From this you can write y dot 0 plus is equal to 1 over m plus y dot 0 minus. Now y dot 0 minus is 0, that is given in the initial condition, so this will be equal to 1 over m. This is also as expected. The velocity after the force is acted is equal to 1 over mass, and this 1 is nothing but the moment of the force, that is the area under the force, which is 1. So we have y0 plus equal to 0 and y dot 0 plus equal to 1 over m. Now we move on to step 2. when we have the equation like this, is equal to xt is equal to 0 for time greater than equal to 0 plus. Now if you factorize the left hand side, you can write it as dy dt, then m dy dt plus k y is equal to 0. If you divide the left hand side by m, then you can write this as 1 and this as k by m. Also, you may like to write this as dy dt minus 0 without any harm. So the roots of this equation will be 0 and minus k by m. This is a differential equation with right side being 0, which we call as a homogeneous equation. Therefore, the solution of this equation will be a combination of complementary solutions like this: k1 e to the power 0t plus k2 e to the power minus k by mt. Now put y equal to 0 plus t equal to 0 plus, so this is k1 plus k2, and if you differentiate this equation, then we have y dot t is equal to, this will be 0 plus k2 multiplied by minus k by m e to the power minus k by mt. Now put once again t equal to 0, 0 plus, so we will have 0 plus k2 multiplied by k by m. Now this value is known to be 1 over m, and this value is equal to 0. So from these two equations, you can find the value of k1 and k2 as k2 will be equal to minus 1 over k, and then k1 will be equal to plus 1 over k. K is the viscous constant. So the final solution is yt is equal to 1 over k e to the power 0t, that means 1, and then plus k2, which is minus 1 over k e to the power minus k by mt, which you can also write by taking 1 over k common. This is the expression of y for time t greater than equal to 0 plus. Okay, so if you now want to plot this function, you can do that. we had the impulse force acting at this point. So that's the input delta t, and let me draw y in red color. So we have 1, so 1 looks like this. Then we have e to the power minus k by mt, so that will be a exponentially decaying function like this. So this is e to the power minus k by mt. This is 1. Now you have to subtract these two, one from the other, and when you subtract, this is the difference between them. So that is initially 0 and then it increases. Finally it gets a steady constant value like this 1. So y will be initially 0 and then it will increase and become 1, and then we have 1 over k multiplied. So if you multiply that with 1 over k, that function may look like this. So this is y equal to 1 over k, 1 minus e to the power minus kt by m. So you observe this is how the float is going to move. Initially it will be at position 0 right after the force is applied, but it will gain some speed, and initially it will have some higher speed. You can see the slope is higher, then it continues to move, but the slope decreases, indicating that speed decreases, and here the speed becomes 0, so it stops at this position. And exactly that is how we saw our float to move in the real experiment. This is also by definition impulse response of our float or this system, because this is nothing but the output when the input is delta t with 0 initial conditions or 0 boundary conditions, initially relaxed conditions. That means 0 position, 0 velocity. So in this way we actually have found the impulse response of our float or of our system. Now we shall take another example. Here we have a circuit with a capacitor C, resistance R, a battery E, and a switch all in series. This switch was initially open and then it is closed at t equal to 0. If that is the case, then a current IT will flow. How that current varies or how the voltage across this capacitor vary, we will find out. But before that, let us just briefly recall the relation between the voltage and current for a capacitor. Suppose I have a capacitor with two plates which has plus Q and minus Q charge. Let the capacitance of this capacitor be C. Then the voltage across this capacitor from here to here, if I call it Vc, with this side as plus and this side as minus, that is my chosen reference polarity. This Vc, you know, can be written as Q divided by C. Now, if there is a current IT coming from left to right, then we can write dq dt is equal to I. The direction of this current and polarity is important. If this current is coming in, then this amount of charge will increase with time. Therefore, I can write dq dt as I. If I is positive coming in, then dq dt will be positive and q will increase. Now, from this expression that Vc equal to Q by C, we can write by differentiating it as ddt of Vc is equal to 1 over C, then dq dt, and dq dt is equal to I, so we have it by C. You may also write it in this way: it is equal to dvc dt multiplied by C multiplied by dt of Vc. Okay, so this is the relation between voltage and current for a capacitor. Here the direction of the current and the polarity of the voltage is very important, otherwise this equation will not be true. Now let us come back to our problem. Okay, so let me first call the voltage across this capacitor as Vc, with this side plus and this side minus. This current IT is coming in from top, from this positive side, like here. So we can write for this circuit as IT is equal to C dvc dt. And if I define the voltage across this resistance as VR, with the left side plus and right side minus, then I can write using Ohm's law VR is equal to IT times R. Now using Kirchhoff's voltage law, I can write this voltage, call it Vt. So using Kirchhoff's voltage law, we can write Vt, this voltage, is equal to VR plus Vc. This is true for t greater than equal to 0 after the switch is closed. Okay. Now from here let me write VR is equal to IT times R plus VC is equal to, I can write, or let me write VC as VC itself. So VC plus VR is equal to VT is equal to E. Okay, this is the system equation. And now using this formula I is equal to C dV dt, C dV C dt, I can write, I can put that here. So I will have C dV C dt multiplied by R is equal to E. This is the system equation. So this is a first order system equation. You may also write this in this way by dividing with RC plus is equal to E by RC. So this is a first order equation. To find the output VC, here VC is what we are considering as output. That means we want to find how capacitor voltage changes with time after the switch is closed. To find this output, we also need a initial condition. One initial condition, we will need the initial value of VC, and suppose the voltage across this capacitor before the switch was closed was V0, then immediately after the switch is closed this voltage will still be V0, because it will take some time for this voltage to change. Because to change this voltage we need some current to come and some charge to accumulate here. For that we need some small amount of time, no matter how small. So initial voltage will be V0. That is the voltage before switch was closed. That is given. Now we will solve this equation, and if we solve, we know the solution, general solution will have two parts. Call it VC1 plus K1 VC0, where VC1 will be a particular solution which satisfies the given differential equation d dt plus 1 by RC of VC1 is equal to the input, and this VC0 will be a complementary solution that satisfies d dt plus 1 by RC acting on VC0 is equal to 0. Now note that this input you can write as E by RC multiplied by e to the power 0t, because this is 1. So we have pure exponential input, and for pure exponential input we can get a particular solution Vc1 in this way: input divided by this differential operator d minus 1 by Rc with d equal to 0. So that will give us E by Rc. Here I have plus divided by 0 plus 1 by Rc. So this becomes E. So this is Vc1 particular solution, and Vc0 a complementary solution you can find for this differential equation as e to the power minus 1 by Rc, because let me write it this way. So the root of this polynomial is minus 1 by Rc, so it will be e to the power minus 1 by Rc t. Okay, so the final solution looks like this: Vc1 plus k Vc0, Vc1 is E plus k or k1 e to the power minus 1 by Rc t. Now let me put time t equal to 0, then the right side is E plus k1 and the left side is given in the question as V0. So from this we get k1 equal to V0 minus E, and so final solution is Vc t is equal to E plus k1 is this multiplied by e to the power minus 1 by Rc t. Now we would like to plot this function time and say the input is constant E. So this is the input. Input is this voltage Vt equal to constant, the supply voltage or battery voltage here, that is input, and this voltage is the output. Now at t equal to 0, if you put 0 here, then output voltage will be E plus this thing, and it is 1. So initial voltage will be E plus V0 minus E, which is equal to V0. Suppose that is here. And at a very large value of time, t tending to infinity, this exponential term will be close to 0. So this term will be gone and we will have only E. So at a large value of time, the voltage, output voltage will be E. And from here to here, it will gradually increase exponentially like this. So this is the output or VCT. Okay, now you may also like to consider this current as your output, and you can ask how this current changes with time. In this case, the quickest way to find the current is to use this formula. IT is equal to C ddt of Vc. So if I do that, let me do it here. IT is equal to C ddt of Vc, and Vc is given here. So we have C ddt of E plus V0 minus e to the power minus t by RC. If you carry out this differentiation, you will get here this will become 0, then V0 minus e multiplied by e to the power minus t by RC whole multiplied by 1 over RC minus, and this is equal to, here C cancels, so and this minus will make it E minus V0, then divided by R, then e to the power minus t by RC. So initial value of the current you can find by putting t equal to 0, so this will be 1. So initial current will be E minus V0 by R, maybe that is somewhere here. And then as time increases, this exponential term will decrease, so current will decrease, and at a very large value of time this part will be 0, so current will gradually become 0, like this. That's all for today. See you tomorrow again. Bye.